So let's say you have a 80 centimeter long string with a mass of 40 grams. Okay, and you're going to put it under, let's say, 1,000 newtons of tension. So 80 centimeter string, mass of 40 grams, placed under 1,000 newtons of tension. So here's what I might ask you. Letter A, what is the velocity in the string? Letter B, what is, let's say, the wavelength of the first harmonic? Letter C, maybe I ask you, what is the fundamental frequency? So if I say fundamental frequency, what does that mean? When you hear the word fundamental, you should think first harmonic. So that would be the frequency of the first harmonic. So instead of saying frequency of the first harmonic, I just said fundamental frequency, but they're the same thing. Okay, and letter D, let's just repeat this. Let's find lambda and F for the first, sorry, we just found the first, second, and third. Okay, so since we're running out of time, I'll just kind of do this, but you guys help me out with the calculations, okay? So to find the velocity, we're simply going to use the equation, right? So the velocity in a string is the square root of f sub t divided by m over L. Just going to substitute in square root of, what did I say, 1,000. Don't forget to convert. Mass was 0.04 divided by 0.8. How much? Make sure you can plug that into your calculator. A lot of people have trouble with that equation. Make sure you're converting. Okay, to find the wavelength. So this is just a matter of understanding your different harmonics and the relationship. So if you recall, the first harmonic looks like this. This is the simplest one. It just vibrates like this. This is my length. How many waves do you see here? Half of a wave. And we'll just plug that in, right? So the length of the string was 0.8, 1/2 wavelength. So my wavelength will be twice that. Remember, it's really long. The first harmonic has the longest wavelength, and it would actually be twice the length of the string. All right, so we know the velocity, we know the wavelength. How do we get the frequency? Use our big equation for the unit, V equals F lambda. So 141 equals F times 1.6. What do you get for F? 88.4. And oftentimes we'll subscript this 1. So F1, what's the 1 mean? First harmonic, yeah. F1 is the first harmonic. Okay, so we'll just let's do the rest of them. So letter D. So we're just going to repeat for the other harmonics. Notice which variable is going to stay the same. The velocity, yeah. So that's just the speed down the string. That's not going to change for the different harmonics. The length and the wavelength are what's changing. Or the length's the same. The wavelength's what's changing, and the frequency's what's changing. So anyway, D. Just recall for a second harmonic, it does look like this. How many waves do you see there? One full wave. So L equals lambda. And since L is equal to lambda, well, that's easy, right? Our length was 0.8, so our wavelength is also 0.8. Okay, so what you could do is go ahead and plug it into V equals F lambda. Or if you conceptualize it, you could do it even faster. Notice what happened to our wavelength. It decreased by exactly how much? 1/2. So if the wavelength decreased by 1/2, what should happen to the frequency? It should double. It should increase by 2, right? So it should double. So you could, if you want to do it quick, you just go 88.4 times 2 equals, is that 176.4 or 0.8? Okay. And then the third harmonic looks like 1, 2, 3. How many waves do you see here? 3 halves. Okay. So notice that this is going down by 1/3, which means what should happen to the frequency? It should go up by 3. Yeah, so F2, notice, is just double. F sub 3 should be just triple. Okay, and if you plug it in like into the other equations, you should get the same thing. This would be 88.4. I can't do this one quick enough. What's the answer? Point what? 0.2, point something like that. Okay, so notice it's doubles and then triples as we start to move up.